What we went through last week was an introduction to what is mobile IP, what problem does it solve, the problem that if we're mobile and we want to continue communicating with using IP, so our application is using the internet protocol, as we change subnets, if we don't change IP address, routing will not be able to deliver packets to us. If we do change IP address, our session will be disrupted and we'll have to stop our session and restart. So to get seamless mobility, we use mobile IP to give us a second care of address. We went through the main mechanisms. So what we started on was going through an example to illustrate them. So we went through forwarding, the issues that arise, how do we learn about a foreign agent when we visit a network, how do we register with a foreign agent, how do we use tunneling, so agent discovery, registration, tunneling, how do we deliver the packets once we've set up or once we've entered a foreign network, and some more advanced things of how do we do handovers between foreign networks as we keep moving, and how do we improve the performance. So the example we're going through is in the handouts that you have. It's this document, but I'm going to go through it on the board. Continuing where we left off from last week. I will leave the network diagram up on the board so we can refer to that, so I don't have to draw it again. Let's zoom in. That's our network scenario, or our network topology in this example. We're a mobile node, or we have a mobile node that was initially associated with the access point 1 on subnet 1110. It had an IP address, 111.100, and as it moved, it needed to hand over to a new access point because the old access point either was out of range or it had too weak of a signal, and it just decided to choose AP2 to associate with. And unfortunately, that's on a new IP subnet, 7770. So it needs to do a mobile IP handover. What we got to last week was, we mentioned the wireless LAN part of it. How do we switch to a new access point? Basically, we need to discover the new access point, associate, authenticate, and then we need to learn about the new foreign agent. F is a router, and it's also a foreign agent for this subnet. So assuming we've associated with access point 2, means we can send packets to the access point. But we know nothing about the subnet yet, so whether it's 7770. So in this document, we're up to section 3 where we want to discover the foreign agent. One thing that a foreign agent may be configured to do is always send route advertisements. So F is periodically broadcasting a route advertisement. This is an IP subnet broadcast message. That is, it's sending to everyone on this subnet. Although it's not drawn on this diagram, there may be other computers attached here. Maybe there's some other desktops and even some other mobile nodes that are attached. So this is periodically sending route advertisements. So if I associate with this access point, I will eventually receive one of those route advertisements. Because I'm associated, this one sends a route advertisement, comes to the access point. Destination address is a broadcast address. So the access point sends it to everyone associated. My mobile node will receive a route advertisement, and once it receives that, it has discovered router F, which is our foreign agent. That's the passive approach for discovery. That is, the mobile node does nothing. It's passive. It just waits for an advertisement. The active approach is the mobile node does something, and what it does is it broadcasts a route solicitation. That is, if this is our mobile node, it sends a route solicitation message, a router solicitation. It's looking for a router to be, in this case, it's looking for a router. It should find router F. So it sends that route solicitation packet, and in figure 4, the structure of that packet, it's an IP datagram. The source address is the special case all 0 address. Because my mobile node doesn't have an IP address yet. On this subnet, it doesn't have one. It has a home IP address from 1110 subnet, but on this new subnet, it doesn't have an IP address. So it needs to get an IP address. So to discover the router, it sends a special or an IP datagram with source address with a special address of all 0s. And the destination address is the all 1s address in dotted decimal 255, 255, 255, 255. Saying, I want to send this packet to everyone on this subnet. I don't care what I don't know what the subnet address is. This should reach everyone on the subnet. And the IP datagram contains the data, which is an ICMP packet. Some students who've taken the lab already this week would have seen ICMP is the protocol used by ping. If you've used ping before, then ICMP is the protocol used there. It's also used for other management things inside a network, including router discovery. So a router solicitation is a special type of ICMP packet. Sent by our mobile node via the wireless LAN to the access point. Access point receives it, notices the destination is everyone on this subnet. Everyone includes sending across this link. So it sends a copy across this link. The router F receives that router solicitation. So F realizes someone is looking for a router and can now respond with a router advertisement. RA. In figure 5 in the handout, the router advertisement is also an ICMP packet. So you don't have to draw these are in the handouts. This is a router advertisement. It's an ICMP packet of a different type to the router solicitation. RS, RA. It comes from router F. And the destination is the local broadcast address. Again, this router advertisement packet is the same what the router sends periodically if it's configured to do so. So router F may periodically send packets like this, 1 per second, for example, saying, I am a router, essentially, advertising its capability. And when a router receives a solicitation message, it also responds with a router advertisement, same structure. So if, for example, the router was configured to send an advertisement 1 every 10 seconds, then maybe in between sending router advertisements, it may receive a router solicitation and send another router advertisement, so that the mobile node discovers at a much shorter interval of waiting for 10 seconds. So two approaches there. In this case, router solicitation, router advertisement. We've now discovered the router. That is, we know its IP address. And it includes, the ICMP router advertisement includes a field that indicates this is a foreign agent. So we've discovered the foreign agent in this case. Once we discover the foreign agent, we need to register with it. How do we register? What's the process of mobile IP registration? What do we do to register? Midterm is in less than 2 weeks, or around 2 weeks. Not long left. What's the process of mobile IP registration? Who starts it? That's the easiest question. Who starts a mobile IP registration? Who initiates this process? Anyone? Which, in our diagram on the board, F is a foreign agent. Here's our mobile node. We have some other entities, some other routers, one of them special. Who initiates the mobile IP registration? MN, the mobile node. That is, the idea, our home network is on 1110. We have a home agent. Router A, in this case, is our home agent. We've moved to a new network, a foreign network. We want to tell our home agent that we've moved into this new foreign network, 7770. So the mobile node initiates the registration procedure. How are we going to draw it? I'm going to remove these packets. Here's our foreign agent, which is router F. And let's also draw our home agent, which is router A in this case. It's typical for the home and foreign agents to be just the routers, the local routers on that subnet. Foreign agent, home agent, with respect to the mobile node. So mobile node has discovered the foreign agent, it now initiates the registration. By sending a registration request to the foreign agent. So this is in figure 3 in the handouts. What does it tell the foreign agent? What's useful to tell the foreign agent? What should the mobile node tell the foreign agent in that request? I'll draw the structure of the packet. That's a P. from the IP header perspective, the source. Who's the source? What's the source IP address of this registration request sent from MN to F? 111,100. That's the only address the mobile node has at the moment. So let's set that. So the source is 111,100 and the destination is the foreign agent address, 7771. And that was discovered in the route advertisement. The route advertisement we drew here had the address of the router. So the one we drew in figure 5 had the address 7771, and this is figure 6, where we're sending from our mobile node to the foreign agent. UDP has some port numbers, and the registration request has some information we need for mobile IP. We need to tell the foreign agent where our home is, so that the foreign agent can forward the request onto the home agent. So some information in our registration request. What is our home address? It is 111,100. That is the home IP address of the mobile node. What is our home agent's address? Is router A. And this diagram shows we're assuming the interface number here indicates the IP address. That is, this is subnet 1110. This number 1 indicates, let's say that the router interface here has the IP address 1111, just to make it simple here. So the home agent is the 1111 IP address. So we need to tell the foreign agent where our home agent is. In this case, we're going to do something for the care of address, is to set our care of address of a mobile node to be the same as the foreign agent. And we'll include that here. Care of address, that is, the care of address for our mobile node is going to be set to 7771, which is the IP address of the router F. It doesn't have to happen that way. It could get a different IP address. Our router is 7771. We could give the mobile node an address 777100, for example, or 7773. It can be different, but in this case, let's see what happens. It's possible to use the same IP address as the foreign agent and see how that works. So in fact, the mobile node has chosen this care of address and sends this registration request to the foreign agent. Foreign agent receives it and is eventually going to send a registration request to the home agent. And we'll see how this IP address, the care of address being the same as the foreign agent, impacts upon or how we handle that. That, or a similar structured packet, is then sent from the foreign agent to the home agent, except our addresses here change. It's now being sent from source 7771 to destination 1111. That is, the home agent is now the destination. Send this registration request to the home agent. Home agent records the data that's received in its mobility binding table and sends back a reply, assuming everything's okay. We've skipped any discussion of the security aspects here. That is, we assume that the home agent knows this mobile node. In practice, there are some other ways to perform authentication to make sure that someone is not pretending to be a mobile node from this home network. That is, some node comes in, some malicious node, tries to join this network and says his home network is in this 1110 network, but in fact it's not. So there needs to be some authentication checks to make sure that everything's okay there. Assuming everything's okay from a security perspective, the home agent will reply. And when it receives the request and before it sends a reply, it keeps or it updates its mobility binding table. Where can we draw that? Which is some database that keeps track of where its home mobile nodes currently are. And in figure 8, we have the mobility binding table after we receive the registration request. We record the home IP address and the care of address. Just a table that records those values. There may be other values, but these are the key things that are needed. And of course, the home IP, when we received the registration request, it was from 111.100, and the care of address is in the packet 7771. This is stored at the home agent, router A in our case. And we're going to use that later because as our correspondent node, the one we're communicating with, sends packets, they're going to arrive at router A. Destination is 111.100. The router is going to look in the mobility binding table and see that, okay, all packets destined to here need to go to some care of address. That's how this is going to be used. So this is created after we validate the registration request. We send back a reply saying everything's okay. Do you have a picture of the reply? Maybe not. Registration reply. In figure 7, there's a picture of the registration reply, but there's a mistake in there. You look in figure 7 in the registration reply, it has an IP, UDP, and then in the figure it says registration request, but it should say reply. That is, this reply is a similar UDP packet containing information saying everything's okay. So it includes the home agent address and the home IP address. When the foreign agent receives the reply, everything's okay, it updates its visitors table. Visitors list. That is the list of mobile nodes that are visiting its network. We're not going to have enough space there. We'll draw it down here. So the mobility binding table is at the home agent. The visitors list is at the foreign agent. That is those visiting the foreign network. Three main things. Home IP, (111.100), that is the home IP of our mobile node. home agent address and the hardware address or the MAC address of that mobile node. We're going to need that to be able to know where to send the packets that are tunneled from the home agent. Recall that what we've shown here is just IP addresses, but in fact the devices also have MAC addresses, layer 2 addresses. Since this is we used wireless LAN in the example, it's got a 48-bit MAC address as well. What it is not shown on here. In figure 9 in the handouts I've given an example. 0017 up to 56. So 12 hexadecimal digits. I've just got an example MAC address. So that MAC address is recorded here. We'll see how it's used when we forward data. Registration reply, foreign agent updates its visitors list as shown here. There may be other things as well. There may be timeouts and so on so that we can delete information later. And registration reply. Mobile node receives this, and from that point on, from the mobile node's perspective, it's now registered on the foreign network and can start sending packets on that foreign network, and should soon start receiving packets on that foreign network. When it sends packets, it uses its home IP address as the source, and when it receives packets, the destination will be its home IP address. But we'll find out that those received packets are actually tunneled from the home agent. Let's see how that works. Any questions so far? You see in previous year exams, for example, a scenario like this and some information given and fill in the IP addresses. So that is, what is the home IP address for this packet? What is what are the steps for registration? That is, what's the destination address for the first registration request, and so on. So you should know these procedures. It's quite simple. Discover, register from mobile node, foreign agent, home agent, and reply, and know the structure of the mobility binding table and visitors list. Yes?
What is
RS. That was a router solicitation. That was, so there were two ways that we said to discover the router. One is the router periodically sends broadcasts saying, I am a router. That's a router advertisement. That's possible. But sometimes there may be a large delay between sending them. That is, let's say it's sending every 10 seconds a router advertisement. I just joined the network. If I'm lucky, I'll receive a router advertisement immediately. If I'm unlucky, it will take 10 seconds for me to receive the next router advertisement. Instead of waiting, I could trigger a router advertisement by sending a router solicitation. My mobile node creates a router solicitation, broadcasts that message. If the router receives it, it will respond with an advertisement. So it's asking for a router. This is advertising a router. Solicitation, to solicit, is to ask for. RS for solicitation, RA advertisement. These are registration requests and registration replies. Any more questions about this diagram before I remove it? We have some time to make sure you know. Any problems? What's going to happen next then, if there's no problems with this? We need to look at how data is transferred. Remember, the idea is that we're transferring data between our mobile node and some other node on the internet, our correspondent node. Yes?
So does the mobile node get new IP address on the foreign node?
In this example, our mobile node has got a new care of address, and the value is 7771. So in this example, it's the same address as the foreign agent. Foreign agent is F in this case. On network 7770, and the one here, we're going to call it 7771. Okay? So that's a special case which is possible. It doesn't have to be that address, but in this case we'll see what happens if it is. Yep.
So what if some nodes in the AP2 want to send data to MM? What address does it?
It can still, if there's someone in here, and so someone else attached to access point 2, what does it know? What address does it know if it wants to send to MN? It knows its original address. That is, let's first consider a node outside. Some node here. We've assumed that it knows its original home address because they were communicating beforehand. They started a voice call. That is, this node made a voice call to here, and therefore they know each other's IP address. So when this one sends packets, it's always going to 111 So we assume that other nodes know the mobile node's home address. How they know is dependent upon the application. Maybe DNS was involved. Maybe this one initiated a connection. Same here. We have another mobile node associated with this access point, 7773, for example. If it knows the mobile node's home address, 111 then what's it going to do? Then it's going to send that packet to 111. Worst case, it sends to here, it's delivered, as we'll see shortly, to the home agent, and then tunneling would be needed. But if the foreign agent is smart enough, and it will, if it sends to 111, the foreign agent will see, here's a special case. Someone's sending a packet to 111. This address is in my visitors list. This node is in my network. We can send it direct back to the mobile node. Let's draw that and make it clearer. We'll go through that example in more detail after we go through the simpler case. Okay, so we'll come back to that example. Any other questions on the registration? Let's go through how the data is transferred and address that question and a couple of others. How do we draw this? Our mobile node, we're assuming our mobile node and this other node on the internet are corresponding. They're communicating. So we'll call this the correspondent node for this example. But it's just some node on the internet. They're sending packets. They were sending when the mobile node was here. The mobile node moved, registered. From the correspondent node's perspective, it doesn't know it moved. That's the idea. The mobility is hidden from the correspondent node. What happens when the mobile node's in the new subnet, in the foreign subnet? we'll go through the data delivery, in this case looking at the data, simplest case, from mobile node to correspondent node. Say we're in a voice call, we're sending IP packets to the correspondent node, then we create an IP packet at the mobile node. What's the source address? Sending from mobile node to the correspondent node in that direction first. What's the source address of this packet? What's the source address? It's sent by the mobile node. The mobile node uses its home address as the source, 111,100. So this is this packet. This is our data that we need to transfer. What's the destination? The destination is who we're sending it to, which is the correspondent node, 888,200. What's the contents of this? Well, whatever data our application is using. If it's a TCP application, maybe accessing a website, then there's a TCP header and HTTP. If it's a voice application, it may be UDP, whatever. But this is the data that we're transferring here. So that's sent from our mobile node to the access point, which delivers it to the router. So that's just over the wireless LAN and the Ethernet. It goes to the first router. And the foreign agent just treats it as a normal IP packet and forwards it on out onto the internet. So when the foreign agent receives this, it treats it as just a normal IP packet. That is, look in its routing table, look at the destination address, 888,200. To reach that, you'd have some routing table. In figure 11, I'm not going to draw them, but in figure 11 in the handouts, there's the detailed routing tables. We see in figure 11, router F in the bottom right-hand corner, that which row in the routing table does it match? Figure 11, router F, which row does our packet match in the routing table? The router at router F. There are 3 rows in the routing table. Which one does our packet match? The third row, the star. In figure 11, let's look at them. I've drawn the set of routing tables for all those routers. And down the bottom is router F. And the simple view of the routing table, to reach this destination, this is the next node in the path. Our destination is 888,200. It doesn't match the first row. It doesn't match the second row. It matches star, which means any other value. So I've simplified the routing table a lot, so we hide a lot of the detail. But that says that the next node in the path is router, or is IP address 6665. And router F sends that datagram to 6665. What is 6665? This network is 6660. This is 2, this is 5. That is, mobile node sends to F, F sends to C, C, if you follow the routing table, will send to who? Who is C going to send this IP datagram to? Look in the table if you don't know the answer. Figure 11, router C has a packet, destination is 888-200. Who does it send to? And D, which row does it match? There are 8 rows in the routing table. Which one does it match? Which row does it match? Destination 888 something. It matches row, the 7th row in the routing table. Correct? The 7th row is destination 8880. We're using that to mean the subnet 8880. This address, we've hidden all the subnet masks, is 888 something. Therefore, send to 4442, which is router D. Send to here. D will send to E, E will send on the correspondent node. Those routing tables just give us the least cost path from source to destination. So it goes along this path. F, C, D, E, C, M. I'll draw that. So that's our data going from mobile node to correspondent node. Uses normal IP routing. There's nothing new about that. Now, be careful. This diagram does not show that it's going to the home agent. If I'm trying to show that it goes to the foreign agent or home agent, I'll leave an arrowhead here. We'll see that shortly. What I'm trying to illustrate on this diagram, which is what figure, is it figure 9? Well, it's got no figure number, but under figure 9 is the IP datagram goes from mobile node to correspondent node via the normal IP route, whichever routers that takes us via. It doesn't have to go to the foreign agent. Well, it will because it's on that local network. It doesn't have to go to the home agent. In fact, it doesn't in this case. That's easy. There's data coming back. How does that work? Correspondent node creates a packet, wants to send it back. Source address. Source address. Source address is that of the correspondent node. Destination address. Destination address. 111-100. Remember, the correspondent node doesn't know that the mobile node is mobile. It's just another computer in the internet. It only knows its home IP address. So now, sending back, destination is 111-100. And we would follow those routing tables in figure 11 to see where that goes. And you can check, but you'll find it goes to E, to D, to C, and then where? The IP datagram, where does it go to? What path does it take? Coming from correspondent node, destination 111-100, it goes to router E, and then router D, and then router C, and then No.
Oh, B.
B. CNEDCB. A. Destination is 111 These routers in the internet don't know anything about the mobility of our mobile node. So they receive a datagram destined to the subnet 1110. They'll keep sending it across the path to reach that subnet, which is over here. So eventually it will come to B and B will send it to A. We'll draw that like, yeah. So it would come to router A, which is our home agent for this mobile node. Router A receives a packet. Destination 111100 checks its mobility binding table. Realises, there's an entry for 111100 in my mobility binding table, which means this mobile node is not home, it's away. It's visiting a foreign network. And the care of address in that foreign network is 7771. So A knows it's not local, it's somewhere else. And it knows where that somewhere else is. So now, the home agent performs tunneling. It puts this IP datagram inside another. Takes this original IP datagram and adds an IP header. What's it set the source and destination as? So this is coming from the home agent now. It performs tunneling, that is, it puts one IP packet inside another. What does it set the source address as? Source address. No. 1111. No. The source is the home agent. Correspondent node has sent destination mobile node. Really, we can think the home agent intercepts that. Or it goes to the home agent and then it's going to send that in a tunnel to the destination. So the source is the home agent now, which is 1111. Destination. Remember, the home agents receive this. All the home agent has in its mobility binding table are these values from a simple point of view. What's the destination address going to be? What's the destination address going to be? The care of address, 7771. He just looks up in the mobility binding table. I just received a packet destined to this mobile node. It's not home. I'm going to send that in a tunnel, that is inside another IP packet, to the care of address. Sends this IP packet onto the internet, that is via the normal set of routers. And if you again follow the routing tables, router A has a packet destined to 7770 network. If you look at the routing tables in figure 11, you should see A will send it to B, B will send it to C, C will send it to where? C will send to where? F. Because the routing tables have been created to get the shortest path from source to destination. destination is here, 7770. So send it across that path to reach there. So it will go to router F. And in the diagram I've drawn this as a tunnel. Which is the concept simply of putting the IP packet inside another. What happens next? Foreign agent has just received a packet, destination 7771. Foreign agent's address is 7771. Okay, that packet is destined to itself. It removes the outer header, and from the inner header, so when the foreign agent receives this, it removes the outer header, it was the destination, sees the inner header, and sees the destination, in fact, is 111100, and uses its visitors list now. Foreign agent received the packet, uses the visitors list to see, okay, we now have a packet destined to 111100. We know this mobile node is visiting our network, so we will not send it back to 111100 out here. Because it's in the visitors list, we know it's local, we will send it to the mobile node here. And that's where we use the MAC address. Destination now, we've just removed the outer header. We've removed this at the foreign agent. So we have this IP datagram, destination 111100. Because it's on the local subnet, we now use the MAC address. To deliver anything on a local subnet, you use the MAC address, the hardware address, to deliver that packet. That is, okay, the MAC address is this 0017, so on, 56. I use Ethernet to send it where the destination Ethernet address is 001756. The source Ethernet address is that of the router, whatever that is. Goes to our access point. Our access point now uses the wireless LAN to send the frame across the link. Destination address is our 0017 address. Source address is F. Access point address is also included in that wireless LAN frame, and it's sent via wireless LAN to our mobile node. So the mobile node receives a wireless LAN frame which contains this IP datagram. For example, what it would receive that'll be the wireless LAN header. If we look, recall the wireless LAN frame has 3 addresses, has other fields, but 3 addresses. The source address will be the MAC. I don't know what the value is. The MAC of the foreign agent. F sent it. The destination address is the MAC, the hardware address of the mobile node, which is our 001756 address. And also we'd have the if this is the wireless LAN, then basically the access point address, which is the MAC of the access point, whatever value that is. So this would be the wireless LAN header for the frame received over this link, sent and received across this link. So that's at the layer 2 level. Mobile node receives it, removes the wireless LAN header, sees the IP header, destination 111.100. Mobile node knows it is 111.100, so the data has reached the destination, removes the IP header and processes the data, sends it to the application. And we receive the data. And importantly, from the application's perspective, the IP address of the source and destination of that packet are the same as when we were in our home network. Source 888.200, destination 111.100. That's the same if we're registered on this foreign network. It would be the same if we were on our home network. It would be the same if I was on some other foreign network. That is, the source and destination address, the IP addresses, do not change from the application's perspective, from the higher layer's perspective. And that's what we're trying to achieve. If they do change, our application needs to restart the session. We don't want that. And that's covered the basic data transfer. There's still one question we need to come back to, but let's make sure everyone's clear on this. Any questions? All the diagrams I drew were in the handout here, except for this header. This is just an example of the wireless LAN frame sent from AP2 to MN, showing the MAC addresses as well. Someone asked a question before. What was your question?
What if a local node in AP2 send a package to mobile node?
So the question, what if another node associated with access point 2 sends a packet to mobile node? That is a node with address this other mobile node with address 7773 associated with the access point sends to 111.100. What happens? What's the answer? What's the answer? 7773 sends it to the mobile node. Sends something to 111.100. Again, we think this is the correspondent node now. Mobile node is corresponding with this other node on the internet. It's just another node. So sending from here to here, we follow this approach. Send via the normal route to the router F, that is send to F. F sends to 1110. Home agent. Home agent looks in the mobility binding table and creates a tunnel and sends it back to F. F removes it from the tunnel and sends it to the mobile node. That's possible. Very inefficient because we've got two nodes next to each other, within meters of each other. The home agent may be in another country. We may have to send it all the way to another country and back. So an optimization is for the foreign agent to realize that. Correspondent node sends to the foreign agent, destination 111.100. Foreign agent checks its visitors list before it sends out to the internet. Realizes the destination is actually visiting my network. 111-100 is here. Do not send it out to the home agent and wait for it to come back. Simply send it directly to the destination. That is, destination is 111-100. Deliver that IP datagram as it is to that mobile node because we know its MAC address. That is, we simply create this frame again and send it there. So we can bypass that home agent in the case. That's a special case scenario. Any other questions on how data is delivered in mobile IP? Let's return to our slides and see what we've missed. We've demonstrated the main mechanisms for mobile IP. There are some special cases, we've just seen one of them, and there are others. And there are some optimizations to make the performance better. We're not going to go through how they work. Of course, there's a problem in terms of delay in this direction. To reach our mobile node, we must send via the home agent. And in some cases, that home agent could be a long way away. An example. An extreme example. Home network is SIT. My mobile node, I'm the mobile user. SIT is my home network. I've moved to another country and I'm using mobile IP. I'm in the US. And some foreign agent in the US I've registered with. And there's a correspondent node I'm communicating with, also in the US, in the same city as me. So correspondent node, mobile node, and the foreign agent I'm registered with is in the same city, same location. On the other side of the world is my home agent. Data needs to go to the home agent and then back to the foreign agent just to reach me. That can mean a large delay in some scenarios, where the optimal path would be to go like this. So with mobile IP, we can get this suboptimal path to reach the destination, which is bad for performance. So there are optimizations to improve upon that, but they require some extra functionality. Gone through registration, how to discover an agent, we've gone through tunneling, route optimization. We're not going to go through these extra features, but they provide some improved performance at some other trade-offs. What else do we have? A handover, where we move from one foreign agent to another, is essentially the same as moving from your home to a foreign agent. We need to register. I'm registered with our current foreign agent, the current one that we registered with before. I move to a new foreign agent. We do the same process. We register via the new foreign agent. We tell the home agent where our new foreign agent is. The home agent would update its mobility binding table. I'd get a new care of address. Potentially, there could be some cleanup to tell the old foreign agent that I've moved. The tables that I've drawn here are simplifications of what is included in reality. At least there'll be some timeout value. That is, only keep this data for 5 minutes or 1 hour, after which delete this, just in case the mobile node leaves and doesn't tell us. So there's some ways to clean up these data, these tables. So there's a handover, which is really just a registration mechanism. How do we know that we're moved between different networks? The same way that we discover networks. If we don't receive any advertisements, and it suggests that we are no longer within range of a current foreign agent. If we receive advertisements from another foreign agent, then I may make a decision to hand over. Same way from our access points perspective. If I receive messages from 2 access points, I may choose the best one. So there are ways to detect movement. And there are ways to improve the handover, to speed up the handover. We're not going to go through them. And that almost finishes for mobile IP. These slides have too big of pictures in them. They're very slow to change the next slide. We have to wait. The last thing we want to say is, well, where is mobile IP used? What's the current status of mobile IP? It's not used in consumer devices. You will not find it on your laptop. Most commercial routers support it. Most routers can act as a foreign agent or a home agent. So that functionality is there, but most laptops especially do not use it. But in some of the 3G mobile standards, and especially in 4th generation standards, they use mobile IP. Mobile IP version 6. Same concepts, but some modifications for IPv6. So it is used in, or will be used in, mobile phones in the future. Home agents support it, foreign agents do, but nowadays you need your mobile node to support it, and not many operating systems natively support mobile IP. But in the future, in mobile phone networks especially, it will be used. That was the host mobility. One device moves between different networks. What if our whole network wants to move? So host mobility, mobile IP, is about my laptop moves from a home network to a foreign network. My network mobility is about my laptop, maybe some other devices in the same subnet, and the router moves. But having a router move is usually not very practical, because a router is plugged into power and has cables plugged into it. So this only makes sense if we have mobile routers, network mobility. In host mobility, the solution is mobile IP. In network mobility, the solution is NEMO. We'll just mention the concept. In fact, most of the principles are the same as host mobility. Host mobility, a single mobile node moves to a new access network. We give this mobile node a care of address in the new access network so it can be reached. That's with mobile IP. In network mobility, the whole access network moves. These nodes and the router moves to a new network. So we have the entire network moving. So therefore, if we want physical movement, these nodes, or this network needs to be able to move. As a result, we need a mobile router. So this router that moves as part of the subnet is called a mobile router. And we may have mobile nodes attached to that, and we may have fixed nodes. Fixed node means it's not necessarily always in the same position, but it's fixed on that access network. The best example is a car. A car can make up its own access network. Let's say we have a special device in the car that provides 3G internet access or satellite internet access. That would be our mobile router. And then many devices in the car connect to that for internet access. All the onboard computing devices on the car, the entertainment system, they would be fixed nodes. In your car, the inbuilt computers and the entertainment system are fixed inside the car, maybe using wires to connect to our mobile router, also inside the car. Then there's you that has your mobile phone. When you come and sit inside the car, your mobile phone is considered a mobile node. It's joined that one access network of the vehicle, which has a mobile router, and these nodes get access to the internet via this mobile router, which then accesses the rest of the world. As the car moves, that whole network is moving. The mobile router may connect to one 3G base station. As it moves, it may need to connect to another and another. So the whole network is moving, so we get network mobility. And there's a protocol similar, or really extends mobile IP, called network mobility, also NEMO. When do you need such network mobility? Mainly with vehicle networks. Private vehicles, you have a mobile router on board that provides internet access to all your devices in the car. Public transport especially, trains and buses. In a train, you have one mobile router that supports a carriage. All the users on the train connect and use that mobile router for internet access. So let's say that mobile router provides a WiMAX internet link. All your users connect from your mobile device using Wi-Fi to the mobile router, which then connects out to the rest of the internet. It's one example scenario. Possibly in personal area networks. You have one device, your phone, which has a 3G connection to the internet. Your other devices you carry with you connect to your phone, tether to your phone, for example, and access the internet via that. So headsets, if you have a music player, MP3 player, or any other device. So you have one device which is the mobile router, the others are nodes that connect to the router. Why not just use mobile IP? Let's see the scenario if we use mobile IP. We have our train, and we have many people with their devices on board, their mobile devices, phones, whatever. So we have 10, 20, 30 people on board wanting to use the internet on that train with their mobile devices. If we use mobile IP, how it works is that there's, let's say, some base station that provides access. They're all using the same technology, They all connect to that base station, which is really our foreign agent. It's our router. So in mobile IP, as that train moves, here's one foreign agent, here's another foreign agent, base station. Then as the train moves, every individual device uses mobile IP to connect to the foreign agent. That is, this one registers with the foreign agent and its home agent. This device registers with the foreign agent and via its home agent, as does every other device. So each individual device handles its own mobility, registers with the foreign agent back to their home agent. If there are 100 devices on here, then we have 100 mobile IP registrations happening. As this train moves, they will all need to register with a new foreign agent when it becomes within range of the new foreign agent. So we have 100 more mobile IP registrations, all back to the home agent. That's inefficient. Having everyone to register via the foreign agent can be done by just one node, our mobile router. So using mobile IP only in this situation can be inefficient. A, it requires all mobile nodes to implement mobile IP. Each of these need to support mobile IP. The signalling overhead is excessive. The signalling overhead is the set of packets sent to establish that registration. Register, reply. If there are 100 nodes, there are 100 register and reply messages. That can be too much. And it normally requires all mobile nodes to have the technology to connect to this base station. Let's say it's a 3G base station. They all need to support 3G. If you don't support 3G, you cannot connect at all. So that's the problems of using mobile IP only then. Let's do it a different way. Let's include on this device a special mobile router. And the individual devices connect to the mobile router. They get an IP address from the mobile router. They can connect via Wi-Fi or any technology that's appropriate there. As the train moves, the mobile router registers with the foreign agent and then to its home agent. As it moves, only the mobile router registers. That is, the individual nodes do not need to be involved with the mobility. They don't care that they're moving. It's only the mobile router that handles the mobility or manages the mobility. It saves on sending many packets to register. You only need one for all 100 nodes. It means only the mobile router needs to support, let's say, this 3G or WiMAX connection, whatever it is. These mobile devices, if you don't have 3G support, you can use Wi-Fi to connect locally to the mobile router or some other technology. You could even be wide links. So we can have various layer 2 technology supported. There's much less signalling overhead. And these devices don't need to support mobile IP. They don't have to be advanced from that perspective. They just need to be able to connect to the mobile router. And that's what NEMO allows us to do. Have a mobile router almost act and do what mobile IP does, but for the entire network. Register, reply, and deal with the mobility. How does it work? Almost the same as mobile IP. The mobile router has some address. When the network moves, the mobile router gets a care of address. With mobile IP, when the host moves, that host gets a care of address, and packets are forwarded to that host in that way. In this case, the whole network moves. The mobile router gets a care of address. It moves to the network Y, gets a care of address, Y dot something, and then correspondent nodes send to the destination XA, and again the home agent tunnels to the appropriate foreign agent here. Same concept of the mobile IP, but now it's the mobile router doing it for the entire network, the entire subnet. What have we got? So we have mobile routers. The nodes attached to the mobile router are called mobile network nodes. These ones, mobile network nodes, mobile router, and the foreign agent or the home agent are referred to as an access router. I think we will not go through any more detail how it works, just introduce the concept of what it is, where it may be used, and why it's needed as opposed to just using mobile IP. Again, we use tunneling the same way as mobile IP, but it becomes a bit more complex. We normally tunnel in both directions, but I think that's enough detail for NEMO. NEMO, or network mobility, a whole subnet moves. The mobile router manages the mobility on behalf of the nodes attached to it. Almost in the same way as mobile IP, registration and so on, discovery, tunneling, care of addresses. There's some extra complexities, but the same concepts. And that's all I want to say about network mobility. Just be aware of what it is, what the advantages and disadvantages are. Who has a mobile network? Anyone? Is network mobility supported today? What's the current status? Again, only in experimental networks. It's not used commonly. In some future vehicles, they have planned or have started to use NEMO and the concepts of network mobility, and future standards are being developed to support that. You can get software that supports it, so there are test beds around, but when you buy a new car, it will not support NEMO. Not yet, maybe in the future. It has been used in some of the details. So used in some experimental and research purposes only. It's been proposed to be used for aeroplanes when they provide internet access to the passengers on the aeroplane and on ships, so on large public transport. It's a standard, although there are improvements being worked upon. There is some software available, some implementations. You can get free software of NEMO available on the BSD variants, but not used except in experimental test beds. Last topic on this mobile networking, the general topic. Host mobility, yeah?
What if we are on the bus and we use the mobile phone as the hotspot?
You use.
Considered to be NEMO?
It can be considered in the concept of network mobility, but not necessarily IP network mobility. That is, you're using a mobile phone as a hotspot, and so your mobile phone has connectivity to, say, a 3G base station out of the bus, and other people on the bus can connect to your mobile phone. That's possible, and you can do that today. But what about giving IP addresses to those other phones? And as you move off the bus, or as the bus moves, making sure that those phones, those other devices, are reachable on the internet. Can someone out on the internet reach their mobile, those other devices? Do they have public IP addresses? Most likely not. So both in mobile IP and in NEMO, the IP addresses are globally reachable. That is, someone out on the internet can reach your mobile device. The way it's implemented in mobile phone technologies today is normally your operator gives you a private IP address. And in fact, that may change depending on where you are and when you connect to it. So that means that no one can reach you if you run a web server on your phone. Why would you run a web server on your phone? Well, maybe not a web server, maybe some peer-to-peer application for someone to connect to. That's maybe more common. So you can do the similar thing of networks that move, but providing this full IP connectivity is not possible yet. That's the difference. If you want to have ubiquitous access, you need anyone to be able to reach any IP device. But there are alternatives. This is not the only way to handle network mobility. There are other ways as well. Any other questions on NEMO? You understand NEMO? Network mobility. The whole access network moves. Briefly, let's just mention this last topic, and then we may have a bit of time to discuss the assignment. Then we'll finish this one today. Ad hoc networking. Let's forget about base stations and access points. Let's say all the students in SIT have their phone or their laptop, their mobile device supports Wi-Fi. Imagine there were no access points. We didn't have access to the SIT wireless LAN. How could we create a network amongst all the students? Well, we could use this concept of ad hoc networking, where the individual devices connect directly with each other from phone to phone. And because there's a limited range for your wireless, that is maybe from one phone to another via Wi-Fi can connect over 10 or 20 metres, if you want to connect to someone 100 metres away, you connect wirelessly to someone within 10 or 15 metres, they connect to someone within range of them, and then you keep going via these multiple wireless connections until you reach the destination. So we get what's called multi-hop wireless networks, or ad hoc networks. Let's explain some scenarios where they're useful. First, everything that we spoke about today in terms of wireless is infrastructure-based wireless networks. We have a base station or an access point, a base station for 3G, an access point for Wi-Fi, same with WiMAX, and all of our mobile devices connect wirelessly to that device, the base station. From there onwards, it's usually wired. My laptop, Wi-Fi access point, and then wired out to the internet. That's the normal mode of operation. The base station is normally fixed. Those access points are connected to the wall, they're not moving. Mobile phone towers are fixed. They're usually connected via wires to other networks. It's usually just a single hop wireless link. The wireless is just from the client device to the access point or base station. These are infrastructure-based wireless networks. They work well because you can design for the performance and coverage. We guess, or a telecom company guesses or estimates the number of users that are going to be around this campus. They put up a tower with enough signal strength and enough antennas and frequency management to support the number of users so that everyone can make phone calls. So it's good to control the resources and design the network using this approach. The problems with such networks is that they are difficult to deploy. Difficult, leading to high cost and a large amount of time. To put in a wireless access point doesn't take long, a couple of hours. It requires drilling some holes and putting some cables to it. Putting a mobile phone tower takes months of preparation and deployment and probably costs millions of baht to deploy that. There's restricted coverage in these infrastructure-based wireless networks. That is, you can only get coverage if you're within range of the base station. Move outside of range and you've lost coverage. And they're centralised. Base station fails, all the nodes within its range fail, cannot communicate. If our access point fails at home, then no devices can connect wirelessly. What's the alternative? Infrastructure-less wireless networks. Have no base station or access point. Connect directly between the clients. So in this diagram, these are all the clients. The red lines are wireless links. They're within range of each other. No infrastructure is needed beforehand. And this is where ad hoc comes from. You just start the network. Everyone turns on their clients, have some software to communicate between them. You don't need to deploy a base station or an access point to start. You can ad hoc create a network. So there's no need for infrastructure beforehand. That's a benefit sometimes. To get large coverage, we generally need multiple wireless hops. That is, A is within range of B and D, these red lines here. Maybe there's a range of 20 metres, so they're both within range of A. But if A wants to communicate with G, they're outside of range. G is 100 metres away from A. So one way we need to communicate is via multiple wireless hops. A sends to B, B sends to C, C sends to G, via 3 wireless links. As a result, B and C are routers. They forward packets. So in an ad hoc network or a multi-hop wireless network, the nodes are normally routers as well as clients or hosts. Nodes move. One characteristic, we have a dynamic topology. I used to have an animation here, no longer. Say a node comes and moves into here, then it changes the topology of our network. We now have a different path. Or B disappears. Then we can no longer send from A, B, C, G. We now need to send A, D, F, H, C, G. Because the nodes are moving, because these are just end user devices, the topology may be always changing, dynamic topology. It's often referred to as a self-organizing network. That is, the nodes organize amongst themselves the connectivity and the different services. In such networks, the devices are normally resource limited. If it's your mobile phone, there's limited battery power, limited CPU, and so on, compared to base stations and so on. And often, in some cases, we may have large networks in this ad hoc nature. Tens of, hundreds, thousands of nodes. Yep.
This one device must have more than one interface.
No. So how many interfaces does a device need in this? A device only needs one wireless interface. Let's say these are laptops, mobile phones, all with just Wi-Fi. They only have a wireless LAN interface. Then how we send from A to G is that A transmits to B via the wireless LAN, and then B sends to C using wireless LAN as well. So they use the same wireless LAN interface. You only have one wireless LAN chip, except you cannot send at the same time. Because when A is sending to B, B cannot be sending to C. Because we know with wireless LAN we can either receive or transmit, not both. So when B is receiving from A, it cannot be sending to C. And that means that the performance in such networks is much lower compared to wired networks and infrastructure-based networks. But no, you only need one interface. You can use multiple, but generally you only need one.
How one process that connects to more than one device? Is this A connected to B, B and B?
When I show those red lines up there, that just means that they're within range. When you say connect, think about not associating with an access point, but having a, in wireless LAN terminology, also called an ad hoc or a direct link between two laptops. So you can have direct links with multiple laptops at the same time. You're not associated with any single device. So A can basically send packets over its wireless LAN to any other device within range. It doesn't associate with one device anymore. Such networks as called ad hoc networks, sometimes mobile ad hoc networks or MANETs, because the nodes are mobile. Wireless ad hoc networks, multi-hop wireless networks, because there are multiple wireless hops, and even other names. When are they useful? When we need a rapid network deployment. That is, we want to set up a network within seconds or minutes. We don't have to wait hours, days to set up a network. When it's too costly to set up the network, it costs too much to put up a base station tower or an access point, and we only need the network for a short time. Let's say we need connectivity between the students outside. There's no coverage from the access points. If we could form an ad hoc network amongst ourselves, it may be cheaper and easier than using an access point. And when network survivability is vital. That is, if one node fails, then the rest of the network can still operate. If B fails, the computer fails, A can still send to G via this other path. That's the idea. If we had a base station, an infrastructure-based network, and the base station fails, no one can send. That's a problem in some cases. What are some examples of domains that use such technology or have such requirements? Came mainly from defence, the military, because they want to set up networks quickly. You don't want to have to wait for a month to build a base station and so on when you're in a war. Sometimes it's too costly to set up the network, and they need network survivability. If the base station fails for the army, then all communications fail. With an ad hoc network, if one node fails, then the others will organise around it and fix so that others can still communicate. Similar with emergency services, there's an earthquake. All the infrastructure is destroyed. You can quickly set up a network using such ad hoc networking. In some business or community or home temporary networks, you need a network or coverage for one day in some remote location, or where you cannot put an access point, then set up a connection between the end users. This is less common nowadays, but these are in use and have been used for years. Some variations, sometimes referred to as mesh networks or sensor networks. Variations of an ad hoc network. A mesh network, some of the nodes are fixed. This is similar to, we put up base stations on all the 7-Elevens across Bangkok, and we connect them wirelessly. No cables, connect all the 7-Elevens via wireless links to each other. Basically, it forms a network amongst them, and we can use that network as a wireless internet service provider. A customer at 7-Eleven connects from Wi-Fi to the local base station, and that connects to other nearby 7-Elevens to provide them internet access between all those base stations. So there's a case where we can replace using the wired infrastructure by using all wireless, fixed wireless links. Because the nodes are fixed, it's not as dynamic as a pure ad hoc network. These networks are in place already today and built across different cities. We have an example network that would, you'll see some of those Linksys access points attached in the stairs in this building and some outside and even in the other building. Some are for our SIT network. Others, if they're turned on, you may see Open WRT as the SSID. That's a multi-hop wireless link. There's 6 or 7 access points where that they connect from access point to access point. They don't have LAN connections. And so on, as a test bed. So you connect via laptop to this one, and that forwards your data via the wireless link to the next access point, to the next one, to the next one, and maybe this one has a LAN internet connection. So you can get access to the internet via these multi-hop wireless links here. And on those, using the software that you're using, the firmware OpenWRT, that supports such feature to connect all your access points together for this multi-hop wireless network. To build, say, community-based wireless networks. Another special case scenario is sensor networks. Normally, we're talking about mobile phones, laptops and so on. Sensor networks, we're talking about very small sensors. Temperature sensors, moisture sensors, motion sensors, and anything that you can sense, some physical environment. Small sensors distributed across an area, a building or a factory or a forest, and they sense data and send the sensed data back to some computer to process it, all via wireless links. So you want to monitor the environment across some volcano. You cannot go and deploy access points and so on. You maybe just drop 100 sensors around the area, small devices which have batteries that run for months or years. They communicate wirelessly with each other and send data that they sense about the volcano back to some central computer. We can do that for different environmental monitoring, agriculture, surveillance and security are some applications of sensor networks. Normally different in that the devices are resource constrained. Very small, kilobytes of memory. Battery that must last for months, if not a year or more. What's hard about these networks? Routing is difficult. Routing, finding the best path through the network, but the network always changes. If a node moves, the topology changes. Therefore, the routing must be very dynamic. So routing is difficult in ad hoc networks. The performance is usually poor compared to infrastructure-based networks. Because we're all using wireless, we interfere with each other and the performance goes down. And there are many other problems regarding security, energy efficiency and so on. Ad hoc networks, good for temporary deployments or deployments where we cannot have infrastructure or wires. Bad in terms of that they're hard to get high performance and to get them to work well. So just some examples of where ad hoc networks are used and will be used in the future. Used in some commercial mesh networks, sensor networks, and been used for years by the military. Not widespread consumer use. You can connect your mobile phone to your laptop via direct connection, but connect phone to laptop onto another laptop, onto another laptop. For that, you need some software installed. You can get software, but not many people use it at the moment. A quick coverage of ad hoc networks, what are they? Some applications of network mobility, how it differs from mobile IP, and of course we've also gone through the details of mobile IP. Next lecture, tomorrow, we'll move on to another topic. That finishes for today.